In this section, we're going to see some pretty unique ideas. They're actually ones that I would have very little focus on if I were testing you. We're going to go through them quickly, and I may skip, but there's a couple of examples I think there's some issues with. So let me just talk you through this. It does require the use of our knowledge of solving equations with logs. Newton's law of cooling. I had never seen this before taking a look at this, but I'll talk you through it again. The idea is this, that if you had something that you just took out of the oven, for instance, and then you place it in the refrigerator, obviously the object after it comes out of the oven is going to cool down to eventually be the same temperature as the fridge. And apparently what happens here is that it cools exponentially. So we've got some different stuff here. T of S is going to stand for the surrounding temperature that surrounds your object. So I took it out of the oven and I put it in the fridge, and the fridge is 30 degrees, or let's say 40 degrees. So if it's 40 degrees, that's the outside, the surrounding temperature. A is going to stand for the difference between your object and the surrounding temperature. So say it was 150 and our fridge was 40. So it came off the stove or out of the oven at 150 degrees. The fridge is 40, so A is going to be 110. It's going to be the difference between the surrounding and the current temperature of the initial temperature of the object. Now everything else there is what we'd expect. We've got e to the kt, where k is going to represent that rate that it's cooling off. Okay, so here's what we got. Something came out of the oven at 165. It's put in a 35-degree refrigerator. So we have a difference here. Our A is going to be 130. Now they did that in kind of a strange way, but so we've got our initial temperature of 130. We know the surroundings. It's now in a fridge that has a 35-degree temperature. What we need to do, just like we did in our last section, is we need to find the value of K. What is that value? Well, thankfully we have a point. We have a value for after 10 minutes, we've got 150 degrees Fahrenheit. So I can plug that in. So 10's going in for time. I've now got a temperature of 150 degrees. We've cooled down by 15. Okay, now all of that's set up to get us to an equation of something that we've been doing in the previous sections. I want to isolate that difficult portion. I want to get e to the k, k to the 10, all isolate. I want to get that part alone, this guy right here. So I would subtract 35, I would divide by 130, and I get this. Okay, well now we know how to get rid of the e by taking the natural log of both sides, then divide both sides by that 10. So I took the natural log, divide both sides by 10, we get down to this. Now if I crunch this, you remember this is just all a bunch of numbers, we could still find that. It turns out to be negative 0.0123. That is our cooling constant. That's the rate at which this cheesecake is cooling down. And so just like we did in the last section, I can then create the entire formula. There it is. Now, they want to know how long is it going to take to get down to 70 degrees. So I can just use our formula, 70. I'm looking for the time to make that happen. We would solve this as we've been doing. We're going to get this portion, the e alone, by subtracting 35 and dividing by 130. Now, we got down to an e, so we can take the log of both sides, divide across, and we're going to get 168, or 106.68. Now remember, this was in minutes. So it's going to take about 107 minutes because all of our numbers were in minutes. So our cooling rate was in minutes. Okay, now I worked this problem earlier, and I think there's an issue with it. And the numbers require taking the natural log of a negative, and I'm not sure what's happened. I don't know if they're wrong or if I'm misunderstanding. I've got a thought on why that is, but again, I'm going to skip that. Okay, now our next idea is the idea of logistic growth. Do I have a picture? I don't. Yeah, let me show you one here. Let's jump ahead. This is logistic growth. So we have some limits here. It's often done in probability, where you can say what are the chances of something happening. When you get to the top, you're getting close to 100%, like can't go any farther. Well, this is useful in problems where there's some limiting value, like there's the max we're going to get. In this case, we can never get above 1,000 because that would be everyone that we'll see that in this story about this town. So logistic means as we continue to grow, we reach a cap and we can't get past that cap. Now, let me talk you through this again. This is not something I've done a lot of either, but hold on, let me take you back to the formula here. So here's our formula where we got some things to work here. C is our limit. Like this is the top number. If you have this, everyone, it's complete, it's full, it's finished. So C is the highest it can go. B is going to be our rate of growth here. So here's our exponential here. We've got the growing going on here with B. And then the C over 1 plus A is going to be the initial value. I can explain that a little better on our next screen. Okay, so we've got this very cumbersome story, but it's about flu entering the town. And there's 1,000 people in this town, so they want to know how long till everyone is going to have the flu, or how many people will have it after 10 days. Well, this is a limiting value. This is logistic because we can't get above 1,000. That would mean everyone in the town has the flu, and that's the most it could possibly be. So that's why we're looking at logistic here. Now, C then is that limiting value. So I've got my 1,000 in there. What else do I got here? So do we have the... Okay, so we've got the growth rate for this strand of flu is 0.6030. So I've got that rate of growth. All we're missing is the value of A. And I think the story is telling us, yeah, at the beginning there's one person who has the flu. So here's what that means. If we plug this in initially, at that initial time, we're left solving this. Here's our initial value. Well, that's 1,000 divided by 1 plus A equals 1 person. So when time is 0, this is all we have to solve. So if this is 1,000 and I solve this doing some algebra, what I'm going to come up with is that A turns out to be 999. Okay, I have all the pieces that I need now. I have got the full formula that I need for this logistic growth, and all I need to do is crunch my numbers. What did they say? We're looking for what it would be after 10 days. Yeah, so we're looking, I think, was it 10? I can't even find it in all that story. Yeah, where would it be after 10 days? So we're putting in an x of 10, crunching this down, and that's where they're coming up with a value of 294. Now they just asked you to do what would happen on day 15. Well, we're just back to our formula again, plugging in a 15 in here for x. So be careful. If you're crunching this on your calculator, be super careful about the order of operations. Use a lot of parentheses or take your time and go really slowly. All right, now I believe the next section is going to talk a lot about this as well. And this is an important idea of mathematical modeling. I think we'll get into it some more detail in the next section. I'm just going to touch on it briefly. So what happens in the real world, this real statistics idea here, you plot a bunch of data points that you've collected from some experiment or some data that you already had. And you'll take a look, you'll create a scatter plot. You'll say, hey, what does this look like? Let me see if we have that. So we've just plotted this. And we're trying to see, well, what kind of relationship seems to be going on here? And the first thing that you would do when you're trying to fit, a mathematical model is just trying to make a math equation fit the real world. So here's my real world data, and I'm like, okay, well, how could math explain this? Could it do it with a line? And if you look at this, no, this doesn't look to be a line. There seems to be some kind of relationship, but it doesn't seem to be linear. Well, how about exponential? Well, okay, exponential grows like this. And if you notice, my curve seems to be going out and about this way. That doesn't seem to be it. And although a logistic could be possible if we had more data points, a logistic would come and start to plateau out, and I don't really see that either. So I'm left with the idea of a logarithmic model. Whatever is going on here seems to follow the pattern of a logarithm. So what we would do is try to solve this here. Okay, we're taking the generic form of a logarithm, and we're saying, okay, well, there might be some stretch outside of the function, a vertical stretch. There might be some kind of horizontal stretch in there on the inside with x, if you remember all of this. So the first thing we're going to do is we're going to plug in that first point they gave us on the chart, 0, 1. So I'm putting 0 in for x, and here's the equation that I would have. I'm putting 1 in for x and 0 for y. This is the equation I'd have. Now, I have two things being multiplied. I have a times the ln of b, and they equal 0. Well, one of these must be the culprit. Well, if I'm making a model and I say, okay, well, maybe a is the reason this is all turning into 0, well, then it would all, a is the initial value. It would make everything 0 forever. So that's not going to be a very useful model. So we're going to assume that is not the case, and that it must be the ln of b that equals 0. Okay, well, remember what that means. It means this: log e of b equals 0. How do I turn e into b? Well, if the exponent is 0, remember a logarithm is an exponent. If e to the 0 is b, then b must be 1. E to the 0, anything to the 0 power is 1. So I can solve that for b. Okay, so here's what I've got so far. I found that b must be 1. Now let's use another point off of the chart that they gave us to solve for a. I just plug in, is what they're doing here, and I solved the value for a. Now that turns out to be about 2. So I have the logarithmic model that we think explains this situation is 2 natural log of x. So the point of a mathematical model is then you could then use this equation for any other value. Suppose you're interested in knowing 2.5, or maybe 10, or perhaps 11. And we've established this relationship seems to be happening here. We could then use this equation to try to make some predictions about values that were not on our chart, which we didn't originally have data for. 5.5 perhaps, 10, 11, anything like that. Okay, now I graphed this on my calculator, and what I got was something like this. Was that right? No, I think it did this. So it did something like this, where it would be logistic, I think would be the best fit. The book actually has this established. They work this as exponential. So I'm not sure what's right. I think visually it appears to be more logistic. I think they left off logistic maybe so you didn't have to try to work it that way. So I think it fits the logistic pattern. But now if you were doing exponential, and I'm not going to work all this through, it's going to be much more difficult because they didn't give us that initial value. Well, I believe we saw some questions earlier in the section where we would solve this twice, where we would need 2 points. So we'd have a b to the x. So I would do it twice. Trying to solve for x, I would have 3.297 equals a b to the 1. And I would do it again for 5.437 equals a b to the second. And you could solve this model by, so a must be, so for instance here, if I solve for a, I'd have a equals 3.297 over b. I could plug that value into this and solve that equation. So it actually wouldn't be too terribly hard, but again, I'm not going to put a lot of emphasis on this. All right, just one last idea here. They want us to turn something into with an exponential base. We want to make it e here. Instead of just being, so our base here is 3.1. We want to turn it to a base of e, and this is really simple to do. What they're going to do is, okay, e to the natural log are opposites of each other. They would just fall out. And so we can make this change by, instead of making this 3.1 to the x, they're going to make it e to the ln and just move that up, because these are technically opposites, so we haven't done anything. E to the ln would drop out and make it 3.1. So I can change this into an exponential base, a continuous base, by just doing e to the ln. I moved everything up. Now, what they've done next is, if you've got the ln of 3.1 to the x power, well, we know the property of logarithms lets us move that x into the front, and then we would have this. Now they just rearranged it a little bit, but same thing. Okay, so simple here. If I want to turn this into a base e, all I have to do is make it e to the ln of 0.5x. These are opposites. Without them, it would just fall back down and make 0.5x. But with them, I'm going to just move it all up. And then we can move that x out in front. And there we go. Okay, again, I don't find this to be a super valuable section for college algebra. I've never needed to teach that before. But there's the basics. Again, for me, a test would not put much focus on that.